Okay, everyone, can you see my screen?
Yes. Yes.
Okay.
Yes.
Okay. Despite all the problem, maybe just like quantum computing, eventually it should work. I know I only have half hours now, so I will need to go fast. However, I do have some resources that you can use. You can go to watch later if you are interested, right? I will go through self-introduction. Originally, I want to have some basics and do a demo, but probably I will not do the demo now and talk about the hardware. But however, I do have a lot of recorded video on YouTube that you can watch later. So I will just give a overall introduction, right? The resources are here. First, I have a book on Introduction to Quantum Computing. I just had the second edition. I don't know about your school. Many schools have subscription. If you go to Springer Link, you should be able to download for free after you connect to the VPN and to your school. And this is basically the first part of my talk, or the first two parts of my talk about quantum algorithm and basic quantum computing. And at the same time, I have this video YouTube link that you can watch, which is correspond to this book. I also have another playlist on the hardware and architecture that you can watch also, right? So if you don't see it, you can email me. I will send you the link. So today I cannot cover all of them. So I hope that you can watch it later or just email me for questions. Introduction, I'll go fast. I'm from San Jose State University in California, in the Silicon Valley, right? In our electrical engineering, we have a master specialization for the Master of Science, right, on quantum computing. Two of them have the playlist that I just mentioned earlier. We also have a quantum technology program for Master of Science in collaboration with Physics and EE, sponsored by NSF. Okay, so what is quantum computing? If I want to summarize it, I will say it is three things. Usually you only say two things. It's a computation based on superposition and entanglement. These are the two most important things you need to bear in your mind. And I also want to emphasize it also based on interference, constructive and destructive interference, just like the water wave. This is because quantum computing, all the quantum state has a lot of information. You actually cannot get all of them in a reasonable time. You need to come up with some smart algorithm and through the interference to get the information you want. So the first thing is, what is state and superposition, right? I don't have time, I just give a summary. In classical computer, you have state, open and short, 0 and 1. Quantum computer is the same if you only allow it to operate on something called basis state, just like the X hat and Y hat in a 2D plane. So you still can have a coin up and down or transistor open and short to represent the same information as classical computing. What makes quantum computing special is that it allows the superposition of states. So instead of just 0 and 1, here you see this so-called direct bracket notation, right? It is basically just something to describe the state of a system. You really don't care what is written inside. So be comfortable with this notation, right? So sometimes people will say a superposition is just like a spinning coin on the table. You don't know whether it's up or down. It's a superposition of head and tail, right? So you can think in this way. But of course, this is wrong, right? But the most important thing is that we can form a superposition of two basis states, which is not allowed in classical computer. So why is such a big deal? If we have many bits in classical computer, for example, 4 bits, I can have 16 states from 0 to 15, right? 0, 0, 0, 0 to 1, 1, 1, 1. If I have a 4-qubit quantum register, I also have 15 basis states. The basis state, like the head and tail. If you have two coins, head, tail, tail, head, and head, right? If you have 4, then you have 16 basis states. The difference is that we allow superposition. Think about that. If I have n qubit, then I have 2 to the power n basis state. So to describe the state, I need 2 to the power n complex number to describe just n qubit. What does it mean? For example, if I have 300 electrons, and then each of them has spin up, spin down, to describe the property, the state of this 300 electron, I actually need 2 to the power 300 complex number or coefficient to describe it, right? Because I can have 2 to the power 300 basis state, and then each state can be a superposition of this 2 to the power 300 state, right? So it is very profound because you see the number of atom or the storage we have in the world is much less 10 to the power 90. Right? So here we have not shown the power of quantum computing, but it already tells us that the quantum state is something very profound. It contains a lot of information. We cannot simulate it or imitate it classically easily. And then what is quantum parallelism? Because I can have superposition of this basis state. This is 00, 01, 1011. I wrote it in the decimal, in the decimal representation. For this state, if I apply a function to it, because it is linear, so I can distribute the function to each of them. So in some sense, we are doing parallel computation. If this works, it's just like I apply an operation, then I have multi-world or multi-universe doing the computation at the same time. And that is true, okay? Everything, everywhere, all at once. Right? This is quantum parallelism. But the problem is of quantum computing is about the measurement. Now, I want to know what the state is. What should I do? I need to measure it. For example, the spin coin, I measure it. It collapses. We call wave function collapse to either up or down, right? So if I have a state like this, again, and I do the measurement, you collapse to either 0 or 1. It's completely random. If I do a lot of measurement, I know the probability is proportional to alpha, the magnitude square of the coefficient. So I will never be able to know what is alpha and beta. Smart method. So we cannot rely on measurement to understand the state. So that is the limitation for quantum computing. Another important thing is the entanglement of quantum computing. Basically, for example, I have 2 qubits. I form a larger space with 4 basis states. I can factorize it so I can describe this total system as a tensor product of the individual system. But there are some states I cannot do that. For example, this so-called Bell state. No matter how you do it, how you rotate the coordinates, you cannot factorize it into the tensor product of 2 individual systems. And this is very important because in classical computer, we can simulate this unentangled state easily, but not the entangled state. Right? So this shows you another important aspect of quantum computing. And we use entanglement a lot in many algorithms. I will skip this slide because this guy was to show some interesting thing about quantum entanglement, but it's not important now because of time, right? You can watch my YouTube. I have explanation. Now, so we know that quantum computer based on the qubit. Then what is a gate, quantum gate? Quantum gates turn out to be something very simple. It's just a laser or microwave pulse. Quantum computer is nothing but just a passive wave function. Your electron sits there with spin a certain direction with certain value. You want to operate it, you shoot a laser pulse or microwave pulse so it rotates. We often map its space to a broad sphere, right? We don't go into the detail, but be careful. Broad sphere is not something in the space we are living in, okay? So quantum gate is like something we rotate the states along the broad sphere to get the results we want. There are some gates called NOT gates or control NOT gate. They have classical counterparts. But some gates you don't have. For example, Hadamard gate. You apply it to 0, it becomes a superposition of 0 and 1. You apply it to 1, it becomes a superposition of 0 and 1 also. But note that 1 is plus, 1 is minus. Here you see that the phase is very important because we're going to use it later for interference to do some computation. That's why I say interference is an important part in quantum computing. Here I will skip because of time. We won't go into the details of the quantum gates, but basically one of the important gate is the control NOT gate. We call it entanglement gate. If you have a few of the important single qubit gates plus an entanglement gate, you basically can implement any quantum algorithm. Okay, then I won't go into entanglement example, but here now let's look at what's so special about quantum gate. One important thing is that it's reversible. In a classical logic gate, if you look at the NAND gate, for example, if I know it is NAND gate, the output is 1, you don't know what the input is because it can be all these 3 possibilities. But in quantum gates, if I know this is a control NOT gate, I know the output, I definitely know the input. Because all quantum gates needs to be reversible. And why? Because they're based on Schrödinger equation. Quantum mechanics mandates that everything is time reversal, right? So this is something important. Another thing is when you see people write down the quantum algorithm, I have a state, apply a NOT gate, entanglement gate, and then maybe Hadamard gate. This, what does it mean? A gate, again, is a pulse. Microwave pulse or laser pulse. It's not a gate like what we did in CMOS logic chip, right? We lay out PMOS, NMOS, NAND gate, or a gate. So this is the flow of time. It just means that I shoot a laser pulse corresponding to the NOT gate. Then shoot another laser pulse corresponds to the Hadamard gate. So when you see this is the flow of time. So if people tell you that there's an algorithm, they need 1 billion gates, don't worry. You don't need to have a large area because you still have the qubits sitting there. You just shoot 1 billion laser pulse, and then you will finish your quantum circuit. And because it's reversible, you can always come back. However, after measurement, as we said, the wave function collapse, you cannot come back anymore. So that is the special about quantum gate. Because of time, we won't do too much about error correction, but this is some important concept we need to understand. First, no cloning theorem. It is proof that you cannot copy a quantum state. Why? It's also easy because how do we copy an information classically? You need to read it and then copy, right? Read it and copy. But reading is a measurement. As we said, measurement collapses the wave function. So in general, you cannot copy any arbitrary quantum state. Now, if that is the case, error correction is a problem because classically for error correction, I can use, for example, repetition code. And then I just have many copies, then use majority vote, I can correct it, right? But what can we do? What we can do is the so-called syndrome measurement. This side is a qubit that we are interested in. We cannot measure it because it will then damage the wave function. So we do entanglement. This is a control NOT gate with some auxiliary qubit. After this entanglement, maybe you go through some error channel, you got some rotation, flipping, and then by just designing it correctly, we measure the auxiliary qubit. If the auxiliary qubit change, we know what happened to our qubit. We just apply the correct gate to the qubit. Again, we did not do measurement. We just correct it. Basically, it's just like this. If I have fever and if the doctor is good enough, he measure my pulse, he measure my temperature. Maybe he already know that I got certain type of disease. So he doesn't need to take my blood. He just directly give me a certain medicine and then I recover. So this idea is like that. So originally I want to go through the process, but because of time, you can watch the slides later. I also have the corresponding video on YouTube. If you want, let me know. We have some discussion. Here, originally, I also want to go through something called Deutsch problem to let you appreciate how the quantum computing can do one-shot calculation compared to two computation classically, right? But The main message here is two. One is that you can do parallel calculation because you form a superposition. You see, we form the psi, and then we do the computation at one shot. Another message is that we actually only know a certain property of the problem we want. For example, in this particular, we want to know whether the function is constant or balanced, but actually we don't know what the function is. Through quantum computing, it helps us to get the answer very quickly, but I still don't know what the actual function is. Okay, I only know its property. Okay. So there's a live demo. I'm not going to do this. Again, I have all this link here. You can go to take a look. IBMQ is free in Taiwan. You can, it's accessible. You can try to go there, implement your own quantum circuit, submit to the real quantum computer. Okay. I do want to go through this slide one more time. So the whole demo, my purpose is to tell you that when we have problem, we need to encode it in a gate called quantum oracle. Okay, we can find the results quickly, but we don't know everything. Okay, so in my way, this is like conservation of information. Yes, quantum computing helps us to get some information very quickly, but it does not help us to get all the information. So we need to come up with a very smart algorithm to get certain information, and then just don't care about the information we are not interested in. Definitely, we need superposition, and we use entanglement in this algorithm. So with this, I will move forward to the hardware part, because Dimensional has 5 criteria about what can be used to form a quantum computer. These 5 criteria are very important. You need to able to separate it into 2 levels. This makes sense, right? Because a qubit has 0 and 1. You need to have that's well-separated levels. Another thing is you need to be initializing. Means, for example, bring it to the ground state. This looks trivial, but it's very important because many quantum algorithms require you to keep resetting the computer, the qubit, to the 0 state. If it takes a long time to reset, then it won't be useful, your quantum computer, right? You need to have a long coherence time, means that it can keep its states long enough so I can do the operation. You need to have a universal set of quantum gate, like what I mentioned earlier. You need to have some 1 qubit gate, not some X gate, Z gate, Y gate, and then 1 entanglement gate, like the control knot swap gate. Then you can basically implement most of the algorithm. And also you should be able to measure them separately. When I do measurement, for example, like the error correction, I only want to measure the auxiliary bit, which is not important. If your system requires me to measure all the qubits at the same time, then it's not going to work. These are the 5 criteria. I will quickly go through in the superconducting qubit, right? This is for communication. We can skip now. So how do we implement quantum qubit? Well, we can use spin qubit, right? Make it in a magnetic field, so they have 2 levels, right? We just talked about 2 levels. We can have photonics, so that the photon can appear on the top of the bottom of the path. It's a superposition, like whether I'm now here in US and maybe a part of me is now in Taiwan. I'm in a superposition state. But because you join the WebEx, I collapse, my wave function collapse to US, you find that I'm in US, right? Now, superconducting charge qubit is like this. We have something called Josephson junction, and then a capacitor. Here is an island. We call it qubit pair island. So here, qubit pair is a pair of electrons, and the information is encoded as whether we have 1 extra qubit or 1 extra qubit pair or 0 extra qubit pair, whether it is n equals 0 or n equals 1. Imagine it's just that, do I have 2 more electrons, 1 qubit pair, or 2 more electrons, right? No, right? So 0 and 1. Use this superposition to encode the information. So first of all, you see that in order to have the 2 level, it is difficult because all these systems have very small separation. For example, here for a superconducting qubit, the separation of the 2 energy is only 0.02 millieV. Our room temperature is 26 millieV. So if the noise is so large, you cannot keep the separation large enough, right? So you may run into so-called T1 decoherence. You put in the upper state, high energy state, it decay very quickly to the ground state. Or you put in a superposition state, it was 0 plus 1, but then the phase got messed up quickly, right? Just like, remember I talked about the Hadamard gate, it becomes 0 plus 1 or 0 minus 1. Then they are completely different. So for example, this superconducting qubit, it has a T1 time of 200 microsecond and T2 time of 19 microsecond. Then it means I want to have my gates to be fast enough, maybe 1 microsecond or less, so that I can have enough operation before the state disappear. So this is the first thing about separating two states. Well, then to create two states, how do we do that? And I completely forgot to mention. So we need to go to low temperature, right? For example, we can use dilution refrigerator. It has a very low thermal energy, or laser cooling in the trapped ion case. So how do we create two states? Why you have this Cooper pair? In principle, you can just use LC tank. At very low temperature, LC tank will be quantized. You can have 1 photon or 2 photon because it's just one oscillation mode, right? The problem is that if I shine a laser pulse to it, which is a gate or a microwave pulse, right? A gate is just a pulse. I can bring it from 0 to 1, but if I shine the pulse again, it can go to 2 because there's a harmonic oscillator. The distance between each level is the same, and that is the problem. Remember, the criteria one is that we need to have a well-defined 1 and 2 state, and you cannot bring it to junction. Josephson junction is a nonlinear inductor. You treat it as a nonlinear inductor. It introduced something called enharmonicity, so that the energy separation between G and E is different from E and F. As a result, you have less chance to bring your qubit to another higher state, which is not within your Hilbert space, in your computational space. What is a Josephson junction? It's just a capacitor, but at low temperature, it becomes superconductor, insulator, superconductor. The main important thing I'm showing here is that it has a nonlinear inductance. The inductance is not constant. It also has the Josephson energy, which is just the same as an inductor. It has its inductive energy. And here, maybe I will just skip, but quickly just say that one type of qubit, superconducting qubit, is that you have this Josephson junction, right, like here, and shrunk it with a large capacitor called the transmon qubit. And now you can see that this is just like what we do in CMOS. You have a layout, and it's just a simple capacitor with this Josephson junction here. Here are the transmission line. So everything is classical. So what does a superconducting computer look like? Here we put the Josephson junction here, and then we have a resonator. Now let's see how we read the superconducting computer. We need a lot of electronics. These are all the FPGA. We just come out with the correct pulse, the shape, correct frequency, correct phase. Then we use a mixer to bring it to the RF frequency, like 5 gigahertz, 6 gigahertz, 8 gigahertz. And then at the room temperature, we shoot the pulse to here, but we go through a lot of attenuator to attenuate the thermal noise, so that when the signal reach here, the noise is less than the quantum noise. And here is 10 millikelvin. The signal goes in, then it's going to come out through some amplification. I will talk about this more later, but the point is that, again, everything is classical. Right? We shoot in the pulse, and then we measure the output pulse. Then we know what happened to the qubit, whether it is at 0 or 1 state. Why? Why we know that when it is at 0 or 1 state? Don't get scared by this, but this is just for some of you who are familiar with quantum QED. In physics, people have a cavity, light cavity. It has a resonant mode, right? We all know that as an engineer. A certain laser frequency can pass through. But you have an atom there. the atom can have a ground state and excited state. Depending on the ground state and excited state, you are going to change the resonant frequency of this cavity. That is called cross-current or pooling, frequency pooling. The only message I want to tell you is that in this so-called cavity quantum electrodynamic, the resonance frequency of this cavity is changed by the states of the atom, whether it's ground or excited. We do similar thing in the superconducting qubit. Here is the transmission line. Again, remember I showed you the micrograph, which is just a layout like what we do in a regular IC chip layout. This is the transmission line. And here is the resonator, right? It only have a certain mode that it can sustain. Next to it, we put a Josephson junction. This is more complicated. Actually, it has two Josephson junctions forming a loop, but just ignore this. The point is the Josephson junction is coupled to this resonator. Like what we did for the cavity QED. Now this Josephson junction is just like an artificial atom. And we can tune it so that we can decide what's the energy of the n equals 0 and n equal to 1. When it is a 0 charge, 0 extra qubit pair, it is going to reduce the resonant frequency of this resonator by negative g squared over delta. If it is at 1, you will increase by g squared over delta. Now you probably know how to measure the qubit. All we need to do is just let the microwave pulse go through it and then measure its real and imaginary part. If it is at 0 state, for example, actually this should be 1, but doesn't matter, right? Here, just treat it as 0. If it's at 0 state, the resonant frequency is reduced. So if I measure at this part, I'm going to get different real and imaginary part than when it was at 1 because the resonance frequency is increased. For example, look at this one. I'm showing the real and imaginary part when the qubit is at 0 or 1 state. The real imaginary part of the scatter wave of the resonator when the qubit is at 0 or 1 state, right? So if I know, if I measure at the middle, depending on the real and imaginary part, I know whether it's 0 or 1. But of course, there are noise. So because of noise, it's difficult to distinguish. So you can see that when we measure in the so-called IQ plot, it is scattering. Now, if we don't do the pulse right, this or the error is very large. This is going to grow, and eventually these two will merge. And if they merge, you cannot distinguish them. Okay. So in summary, I just want to say that to measure a qubit in superconducting qubit, we rely on this pooling or the cross-current, the change of resonant frequency of the resonator due to the state of the transmon qubit. Okay, so of course here you can say you see that I can measure individual qubit, right? I just need to have different frequency multiplexing or just put them apart. So I satisfy another criteria. How do I have a single qubit gate? As I said, single qubit gate is nothing but just that rotating the states on the broad sphere. You can see that it's just like this matrix, right? We won't go into detail. But the thing I want to tell you is this. Again, we cannot go into detail because this takes a long time, right? Even originally, I don't want to go in detail. But I just want to show you that if you go through the math, the Hamiltonian, which govern how the qubit evolve, actually can be abstract as like it has an effective magnetic field. This is a fake one, fake magnetic field, and as it has a spin, just like in a spin qubit. And you see that then it depends on the EJ Josephson energy I told you earlier, and also EC, which is the capacitive energy. And then what we do is that we change the pulse magnitude, eta, and also the phase. You will find that the final Hamiltonian depends on this, and it depends on what? Delta, which depends on the frequency, the Josephson energy, and the capacitive energy you have in your qubit. It also depends on the charging energy and the phase of your pulse. All I'm trying to say is that if you go through the math, how the qubit evolve on the Bloch sphere completely depends on the phase, the magnitude, and the frequency of the pulse you send in. So you just do this right, you will get the gates that you want, because what is a quantum gate again? It's just a microwave pulse. So I just manipulate the microwave pulse, then I will get the gate, right? Here is an example of implemented lock gate, NOT gate. We also need entanglement gate. One possibility is like this swap gate in superconducting qubit. Won't go into detail again, but you will just, this is again, 2 Josephson junction. You are going to have the flux going through here to tweak their resonant frequency. When we want to implement the swap gate, we just make the flux correct so they will start swapping energy. Okay, and you will get this gate automatically. Okay, so I think I rushed pretty fast, but what I want to say is the quantum computing is very profound, right? You get a lot of information. And this is the problem. I have 2 to the power 300 coefficient. Even getting this information take you a long time. You need to do 2 to the power 300 measurement and even more because of statistics. So basically it's useless if you try to get that. But you come up with some smart way through destructive or constructive interference, for example, to check if the function is balanced or to find what is the period of the function. We never try to find out what the function it is, right? We just find the period. This is used in the Shor algorithm for decryption, right? Then we can get the answer we want. So quantum computing cannot replace classical computer just because of its nature, but it's a very powerful accelerator, such as for the optimization problem. Yeah, so finally, advertisement again. Many of these are taught in these classes. There are 2 playlists, and then this book you can take a look. Again, you can download for free, probably from your school if you use school computer to Springer link. Okay, yeah, so that's all I have, and I acknowledge the support from NSF and our collaborator. Thank you very much. I think it's about time.
Yes, okay, thank you very much, Professor Wong. Yeah, sorry for all the inconvenience that it's just now, because it's the first time we set up this international quantum computing free online forum. I think we still have a couple minutes. I think there is time for open for the question. So if you like, you can open your microphone and or you can type your question in the chat box. Yes. Now, maybe let me ask 2 questions first. The first question is, I'm always wondering the multiplexing technique, because I'm not a hardware people. So my first question is, how can the multiplexing allows us to reduce, to collect a large amount of detecting a signal using only a few cables? And the second question is about the implementation of the single qubit technology. You said you can think about that the evolution of the qubit on a Bloch sphere is something you can simulate a single quantum gate. So that means that by changing the amplitude or the phase of the LC, the Josephson junction LC circuit, you can manipulate the evolution of that qubit on the Bloch sphere. So it means you can simulate all possible single qubit gate. Yeah, this is my two question.
I'm very sorry. I got kicked out 2 times when I tried to. Yeah, can you say again?
My first question is, I'm always wondering about the multiplexing technology. Why it can reduce, it can collect a lot of detecting signal using the multiplexing technology. And the second question is about the implementation of the single, single qubit. Is the evolution of the qubit on the Bloch sphere. So does it mean that you can assimilate all possible single quantum qubit? Yes.
Yeah, so I don't know if I understand correctly, but for your first question, right, for multiplexing, if you try to tune the qubit at different, what we call the qubit frequency, the 0 and 1, right, you can have different EJ, then you have different frequency. So in that case, you can just shoot a multiplex pulse, right, with using multiplexing, and then you will detect all of them at the same time, because they all have different resonance frequency. So there's a way to do the frequency multiplexing.
Oh, okay.
Yeah. So you don't do the identical qubit. And then for what you about the single qubit gates, yes. Let me see if I can share, because every time I share it the computer die. But in the single qubit case, right? Let me see.
Right. You still have the privilege to share your desktop. Yes.
Yeah.
Yes. Go ahead.
Yeah. So for the single qubit case, well, basically what you want is to able to impedance as long.
Hello. Hello.
Maybe Professor Wong got a network problem.
Okay. So let's wait for a few seconds. Oh, he also get removed from the section.
Network down. Yeah. Maybe we should wait 3 minutes when Professor Wong come back. Otherwise, we will close the section.
Okay. So now it's 5 minutes past 12 at Taiwan, the local time, right? So let's wait for 2 more minutes. Let's see if Dr. Wong can join the section again. Somebody texting me. Let me see.
Hey, sorry, Dr. Ng.
Yes.
I'm okay now. Yeah, sorry.
Oh, okay.
Yeah, I cannot share the screen because it always crashes. But basically, I show you that you have 3 parameters, right? And you can just control the phase, the frequency, and then you can change those parameters. Then you can rotate at any space. Yeah.
Okay, so that we'll be able to simulate any single qubit gate.
Yes, to implement any single qubit gate. Yes.
Okay. All right. Good.
Mhm.
Dr. Wong came back. So, any questions from the audience?
I want to ask,
Yes.
how to make sure the qubit is entangled?
Okay, so you can form entangle by using a Hadamard gate and control NOT gate, right? So to do entanglement is easy. And now your question is how to make sure it is entangled. Probably you're talking about continue to be entangled. Then this is related to the decay time. In this process, you can have error that you change the phase. That is one thing. Another is that it can have some flipping. Right? Actually, for all error, you can think all the error as a gate. Actually, it's just a gate that you don't want. So you can introduce different error and then so that you will start disentangle gradually. Do I answer your question? So instead of like make sure it entangle, it's just the same as how can we make sure that it doesn't accumulate too much error.
Oh, I see. I was just wondering, when we are building a quantum circuits, they must be entangled so that they can perform like a quantum circuits, right? Yeah. So yeah. I was just wondering, when we build all kinds of the quantum circuits, how can those scientists know the entanglement already built up?
Oh, okay. Okay, you mean how to check if it is entangled, right?
Yeah.
But usually we don't check. Usually you just assume it is. But however, then you might have accumulated error. So then in this case, you will have error correction to make sure that the error can be corrected. And if you say, how do I know if this state is entangled? It's almost impossible because if you want to measure it, it will collapse right away, right? So unless you prepare a lot of identical pair and then you just measure it for 1 trillion times, then you say, okay, looks like it is entangled. Otherwise, you don't really try to check if it is entangled. It's like after maybe a certain operation, you look at the results. If the result is bad, because you rely on superposition and entanglement, and then eventually interference to have a large signal. Only after that, you will see maybe something wrong happen in the circuit. But whether it is due to the entanglement or others is difficult to know.
Professor Wong, is there something like 50% entanglement or 100% entanglement or 10% entanglement?
Now, this is the so-called entangled state. So it has something called entropy, entangled entropy, to measure whether a state is entangled or not. So it has something like what you say, 100%, we say fully entangled, purely entangled, or maybe 50%. This is the entropy, right? So there is something like this. Yes. Okay, but this is mostly try to describe a state. Of course, when you start losing, become decoherence, then you can also do that. But experimentally, it is, I mean, in a circuit, usually you don't try to measure whether it is entangled, because every measurement is going to collapse the wave function. Then everything will be gone.
I see. It's amazing.
Okay, all right. Hello, can you hear me?
Yes.
Yeah, yes.
Okay, all right. I think it's almost close to the end of this presentation. So I think we are going to close it. And
sorry, Professor, can you give me the PowerPoint?
I have to ask the speaker's permission about the PowerPoint after the talk.
I can
Yes.
send you, Professor. I can send you the
Okay.
PowerPoint, then you please help to distribute.
Thank
Okay,
you. Thank you, Professor Wong.
Yeah, and then we will put up the video later, and I will notify everyone, say hopefully within 5 days after the talk. All right. So again, I'd like to apologize for all the inconvenience that we incur during the beginning of the section. So so thank you again for your participation. We will have another talk coming up, and we will announce it and keep you informed. So thank you, Professor Wong, for your time. I know it's the evening at the US, so have a good evening. All right.
Thank you very much.
I want to ask one thing is, if I have any problem, can I email you, Professor Wong?
Yeah, sure. Yeah, feel free to email. Yeah.
Yes. Thank you very much.
Okay. All right.